I would like to present about one baseline of Tuan's model paper. So this one is meta graph based recommendation fusion over heterogeneous information network. This appeared in KD 2017. And so why I choose this paper? There are three reasons. The first one is it's using the HIN network as an additional information to learn the rating prediction. The second one is it is considered the rating prediction as the main task, so they based on the minimize the root mean square error. And the third one is this one is second best baseline compared against the paper model, and which published in very good conference is KD 17. Okay, actually I quick introduce again about the HIN network, Heterogeneous Information Network. So it's kind of the knowledge graph. We have some node and have some link between relation between these nodes. And here we consider it's a graph of set of node and set of edges, and correspond to the HIN net. We have a schema is a G here. We now regularly we consider the specific node. We group node in some group type group of node, or maybe call it a node type. And we also group on the relation in some we call it edge type. Okay. So for the meta graph in here, let's say I introduce two examples. I think I will not mention again because Tuan give very intuitive example for this. But the idea is we try is a directed accurate graph with a single source node from, let's say from source node is the user and the target node is the item. Okay. In this paper, they consider two main data set, and in the JEP they consider 9 different types of meta graph, and in Amazon they just consider 6 types of meta graph. Okay. So actually the main idea of this one is kind of a pipeline model. The first one, when they have some user information and item information, and with the HIN network, they will based on this to compute the similarity between a pair of user and items. We call this meta graph based similarities. And after that, based on these similarities, they will learn some of the latent features for each user and item, but respect to a particular meta graph type. And after that, they've been based on these latent features and apply them factorization machine to predict the ratings, and using the rating to make recommendations. Okay, this is the pipeline model. I will not like to go more detail in the next slide. Okay, for the meta graph based similarities. So this one is also based on the pairwise like Tuan's model, but in a different way. It means that here they don't use they don't compute the similarity, but they use the adjacency metric between the two types. Let's say for this one is the adjacency metric between the user and the business. Business is integer, and they will try multiply along the sequence, the meta part here, and after that we got is this one they call it the commuting metric that represent the relationship for U1 and the B2. Okay, and this one is another example. Is more complex meta graph. It means that here we from U to B2, U1 to B2 here we can have a two different two different meta part. So they propose the respective solution for this. It means that they compute this sub part first, or this compute this sub part, and they try to aggregate the two sub part and along the meta part. And Actually, this one is one example. They based on the commuting matrices here to compute the user item similarities. They based on this this equation. So I mean that for X metagraph type, we can compute a similarities metric. Okay. So if we have L metagraph type, we can have L similarity matrices. So as I mentioned before, for in the JEF they consider 9 metagraph, and Amazon is a 6. So okay. This one. So after this part, we will have some the similarity matrices for every pair user and item. Okay. So for the metagraph based latent features, after we got here is a similarity matrix. After they got it, they will try to learn the latent features or latent representation for every user and items, or user and business in the context of geo. And for L metagraph, so we got L group of latent feature or latent representation for X user and items. Okay. And they will use this representation to represent one instances of user and item. Here I mean that the input can be is constructed by we just concatenate on the latent representation respect to the metagraph type. So this one, the first one is for represent for the users. The next L times F is represent for the business or the items, and X element here have is the F dimensional vectors. So here this is the input, and after we got this, they will apply the factorization machine for the rating prediction here. The idea here means that we not only investigate the importance of every single latent feature here, we also want to consider the interaction or the associations between these latent features. Okay, and after that we can predict the rating of the user I of a given J, and after that we apply the optimization with some regularization. Actually, in this paper, they introduce some we call the group layer regularization, but I will not go to detail. And the complexity of this optimization is the OTNKLF. T is the number of iteration, N is the number of rating, and K is the latent dimension here, and LF is the number of meta part, and F is the latent representation for X respect to a particular meta graph. So this one is the overall architectures of the baseline model is a FMG. Okay, so I want to change to the review question. I have 5 questions, but I think it's not difficult. And the first one is actually commonly I also only see, let's say they have only one layers attention, and after that let's say this is based on the equation 6, and then that they compute attention. But why here they use the two layers, and after that they're using the second score to compute the attentional weight. So this one is not clear, so any explanation behind. Okay. The second question is actually I'm not clear about the intuition why they use the context-based meta-graph context-based vector here, and to improve the representation of for the user attention and the item attention. It's not what the intuition behind. I'm not clear about it, because actually this okay. The third question is in the paper they mentioned that for each meta graph, they just assemble 5 path instances using the SPD features. But they don't vary, I mean, so the experiment that way, they vary the number of sample path here. And so I'm wondering that it is enough to cover the important case. And let's say now for the 2 node, maybe you can have many meta path. So if we take this 5, maybe we lost some important part. Okay. The fourth question is, they consider is very small setting of L and the length and the number of meta path and the number of maximum of path indices. So it is considered a limitation of the proposed model because maybe we have more complex part and we have a larger number. So how it can deal with this? And the last question is me that I want to know that the incorporating order here is the matter. Why they show this order? Why is not the other order? And I think this one to clarify the importance of the different metapath type. Okay, that's all. You have any question for me in the?
Yes, we have some time. Any questions for Trong? No questions.
So in this model, then they also weight the importance of the meta part in predicting the ratings, right?
Yes, but I mean they use all the meta part. We don't just pick the top meta part because they will based on all the meta part to compute the similarities between the user and item.
So, okay, in some way it is like the attention weight in advanced model.
No, it's not, because here for every they can compute the commuting matrices for every meta graph meta part type. So that's why after that they will based on that to compute the similarity. So I mean that they use all
but in the factorization machine,
what are the features?
This one is the features, the latent features.
They're gonna weight the feature.
So just users and items?
Yeah, user and items.
Any other features?
No, I mean this features come from this meta graph based latent features, and this part is just try to predict the rating of the user on item. And this one is the latent features. It's not. It's not. It's kind of
It comes from the meta part, right?
Yeah.
And
Which one comes from the meta part?
This
The
part.
different U and different B. Each of them come from different type of meta parts.
Yes.
So
Yeah.
the L is the number of meta parts.
L is the number of meta part. Yeah. Number of meta part type.
Number of meta parts.
Yes. Yeah. In some ways, similar, because this one they will learn the weight for each vector here, and this one is the isolation interaction, two-way interaction between the two different latent feature vectors. But I mean that is the automatically learn from all the data, all the meta graph, not like pick the top like on paper.
No, let's carry on with review.
Okay.
So,
Okay, thank you, Trong, for your questions.
let's give Trong.
Yeah, let's. So you told me you asked one question. So which one? Which one of the 5? All right. So the first question, right? Why use 2-layer attention architecture to model meta-space context? Okay. So basically, your concern is why you 2? Why not 1, right? Okay. So firstly, this is not the only one paper that uses 2-layer to calculate the attention score. I can show you some other papers that they use too. But this is not the main point. I guess here their concern is that they have multiple types of input to calculate attention. For example, user, item, and the context. So I guess the hypothesis is that they need another layer to better combine those features to calculate better score. Because most of the time, normally when we do attention, let's say over text, we only have 2 type feature, for example, the query and basically the set of the feature that we want to attend on. And here they have items. So I guess because there are a lot of type features here, so why they do another one. So I'm not sure. I mean, I'm not sure they try with 1 layer or not. Maybe they try with 1, but they try with 2 and they see 2 works better. But they don't explain on this part because this basically they are not the first one who do that.
But they didn't sign in the paper, so if they sign someone,
I mean, you predict score, right? You put the layer of MLP and you put 2, you put 3, you put 4. It's the same, right? You don't need to explain like why I put 2, I put 3, I put 4. I just say that this give the best performance. That's why I put this number of layers. So this one basically the same. There is no standard way to do attention, and this is just one way to calculate the attention score. So I guess is this. What is the intuition of beta? Okay, so yeah, basically without this part, we have the model without a user and item attention. So this part is the user and item attention. So I guess the intuition here is that the C here is the context that learns from the user and items, and basically this context already encodes some type of information between user and items. So this is another operation to combine the features before they fit into the MLP. So possible they try to reweight the factors. So let's say in your user side, you know the item information encoded inside this context, and you might want to reweight. So for these items, some of the dimensions in the user embeddings are important, some are not. So possible is the reason why they try to reweight the embeddings of user before they fit into the MLP. So it's a different type of interaction compared to the MLP model after this one. I guess it's the idea. Yeah. Why are only 5 metapath sample? It is enough to cover important cases. Okay, so this is after they calculate the score and they rank based on the pairwise similarities of the path instances. And for each metapath, they're gonna take top K based on the score. So what they claim is that this is the better instance than the other ones, and they pick the top K is, I guess, arbitrary. Is reasonable numbers to do computation. If you are fortunate enough to sample 10, then I think in practice you can do, but here they just set it to 5. And this one is the number for each metapath. So you have multiple type metapaths. Let's say you have 4, 5 metapaths. So between user and item, you possibly have 20 path instances to learn the context. So I guess it's a reasonable number. Maybe not.
Why 5?
This is also depends on the property, the characteristics of the network. Is it dense or not? Is it sparse? Can you sample enough instances from the network? So this one is also depends on the data. So this I'm not sure. But 5, I guess, is they do experiments and they see a reasonable number. Because between user and item, maybe you cannot sample enough 5 instances. And it is a limitation of MC reg. Okay, so I guess Andrew already asked about this. Yeah, basically, if they, because of the ranking path, because of the so if they random sampling, so they don't need to care a lot about the length and the number of meta paths here, but here because they want to rank, so possibly they need to sample all the instances and they calculate all the score for all the instances and they rank, they take top K, so that's cost a lot. But the main claim in the papers, they says that all the training are offline, and they analyze some complexity, and they said that this are offline training and you train once, but then in the inference, when you recommend to use an item, you don't need to redo the process of samplings and learning the embeddings. So this is gonna save time, and this part only costs when you train the model offline. So that's the main claim.
But they only use for offline training, right? For 3 data set, they just consider, I think, 4 types of meta path, right?
Yeah, but when you recommend when you calculate the score for user and items, right? You already have the context embedding between user and item, so everything already learned. So you only need the MLP part to basically infer the score. So the embeddings of user and item and the context between the user and item are learned offline.
So it is a limitation, or not?
Yes.
Yes, for but it's computational is the claim here is that this costs the computation offline, but for online it's not a limitation for the recommendation. So does the incorporating order matter? Yeah, I guess yes. You're gonna have different line when you reverse the order of this, but
And another one is to this one is and you show them. I mean, you say investigate the importance of different meta graph.
yes.
You show there are some is more important than the others,
Yes.
right? Because bigger, larger attention away. But why? I think here
I think they show the same order.
No,
They show the same order as they show in the
no,
huh?
no. The second.
So this
the
one
second is
movie
the
lens,
second-
right?
movie lens, the second is the best.
UMGM
UMGM is the best.
for movie lens.
Yes. And for Jeff, this one is the best.
Yeah, I mean the order that they show here is the same as the one they show in the paper, is it?
The same order, but I mean,
UM, right? UMGM. Same as the one they show here, right? So I don't know how they comes up with this order, but they just follow the same orders for all the illustration.
because it's the way, I mean, it's an increasing chance, right?
So why is it aligned?
Why is it aligned?
Why is there aligned? Why not just a bar chart? So that means the implication is that there is a relationship.
Well, maybe a mistake when I draw a line there. Yeah, you can show a bar chart here. I think bar chart is more appropriate for this case. Yeah, but the point here, they want to show that basically adding more type of meta paths actually improve the model. Because this order, I mean, the order doesn't make sense because you don't have any order here. Any order are possible.
So this is the last question.
Yes.
Is it?
Yeah.
So are you satisfied?
So,
You satisfied with the
Yeah. So.
So
so can you go back to your own slide that compares to his method?
okay.
Below.
Where's the
Okay.
compared to the method, the results, right? This one.
So which one is it?
FMG.
F.
This one.
FMG. Okay. And which is good, right? So what is the MC rec? The
MC rank is a mono, proposed mono.
Okay.
So this one is a random sampling.
Uh-huh.
This is the SVD feature. Those three are the SVD
means
feature.
just any path.
Yeah, any path.
Okay.
This one, those three are basically already ranked. The path instance already ranked. But this is the averaging over the meta paths, the embeddings. The MP here is the path attention, and the final one they add the user and the item attention.
The MP is what again?
The MP is the path attention,
Path
without the
attention.
user and the item attention.
And the star means
Just that.
This which one? This one?
the star.
This one. This one they show the best performance across the baseline. It's just to indicate the highest number.
Okay.
As baseline.
So in why would MC do better than the FMG?
Why?
Average attention.
I don't understand the FMG paper actually.
Actually, because maybe in the FMG paper they mentioned that maybe there are some meta part can be covered by other meta part.
Yeah. So
So-
you present the columns, right? The L
Yes.
columns. Each one is corresponding to one meta.
Yes.
Okay.
So here, I mean, maybe we have to provide a better way to the attention in some important part or important part and important information.
In what sense? Because the attention is on the path, right? So which path is more important?
Yes.
So then for the FM,
For your case, already learned through the FM.
yes.
The FM
So
learn the attention.
in fact, they know what is the importance of individual meta path
Yes.
and what is the importance of any two path interactions.
Yeah.
So in some sense, they can also learn the relative importance of the path. And in fact, it's over all the possible paths, not just over the sample of 5.
Yes. So maybe because of that, they have you consider a lot more part. So maybe making some noise or some like the conflict.
So you're defending his paper.
Yeah, I'm depending on it. Yeah, maybe. Yeah. But actually,
Uh-huh.
okay, guys, don't use my statement and
Disclaimer.
I think in my opinion, I think his paper is more reasonable.
Wow.
So we don't need to vote, right?
Yes.
The reviewer with me, so you don't need to vote.
So actually, because it's kind of the end-to-end framework, but for the other one is the pipeline. It's not. But I don't know why. Because maybe they have some.
So you don't like that line?
Yeah, I don't like why because this
You like
input.
end to end.
Yeah.
One button, click.
Just so.